Hello dear students, welcome to mathematics class. In this class, let us discuss some theorems on function of a complex variable. So here the first theorem is Cauchy's theorem or Cauchy's integral theorem. Cauchy's theorem or Cauchy's integral theorem. The statement of this theorem is if f of z is analytic at all points inside and on a simple closed curve C, then integration over C f of z dz is equal to 0. So here f of z is a function of a complex variable which is analytic at all points inside and on a simple closed curve. So here simple closed curve means any for example a circle is a simple closed curve because here the structure of the circle is closed because where the point or where the curve starts, at the same point the end point will be there. So therefore that is the meaning of the simple closed curve, means there is no overlapping of the curve and there are no loops in that curve. So that curve is simple closed curve. Then here integration over C f of z dz is equal to 0 means the area under that closed curve with respect to the function f of z is 0. So let us prove this one. So for the proof of this Cauchy's theorem, we require one more theorem that is called as Green's theorem. So here the definition of Green's theorem is required. So let us take the statement of the Green's theorem. So here if p of x comma y and q of x comma y be two continuous functions satisfying first order partial derivatives in a region D consisting of points within and on a simple closed contour means curve only. So on a simple closed contour C of domain D, then integration over C p dx plus q dy is equal to integration over D. So here double integration over D dou q by dou x minus dou p by dou x into dx dy. So here this is the Green's theorem. So therefore here whenever there are two continuous functions p and q, then integration over C means with respect to the closed curve C, p dx plus q dy is equal to double integration over D dou q by dou x minus dou p by dou x into dx dy. So let us continue with this one. So here it is dou p divided by dou y, not dou x, dou q by dou x minus dou p by dou y into dx dy, because there are two variables x and y. So therefore consider the partial differentiation of q with respect to x and partial differentiation of p with respect to y. So now we will use this statement while proving the Cauchy's theorem or Cauchy's integral theorem. So here let us prove this one. Let f of z is equal to u plus iv, where u and v are the functions of x and y. Then integration over c f of z dz is equal to integration over c f of z equal to what? U plus iv, and dz becomes dx plus I dy, because we know that z equal to x plus iy, then dz becomes dx plus I dy. Then this is equal to integration over c. Now multiply these two, that becomes u dx plus I into u dy plus I into v dx. Here I into I becomes I square, that is equal to minus 1 v dy. So now let us separate the real and imaginary parts. So therefore that becomes integration over c. U is a real part and minus v is a real part. So therefore here u dx minus v dy plus I into remaining u dy plus v dx. Then this is equal to integration over c u dx minus v dy plus I into integration over c v dx plus u dy. So here we have separated the integrals and consider this as the first equation. Now by applying the Green's theorem, so here in Green's theorem we have two functions p and q, which are the functions of x and y and which are continuous. So then integration over c p dx plus q dy is equal to double integration over d dou q by dou x minus dou p by dou y into dx dy. So therefore here we will apply the same one. So integration over c p dx plus q dy is equal to double integration over d dou q by dou x minus dou p by dou y into dx dy. So therefore equation 1 becomes integration over c f of z dz is equal to double integration over r. So let us consider here region as r instead of d. So double integration over r into here u dx minus v dy p dx plus q dy, means q is equal to minus v. So therefore this becomes minus dou v by dou x. Then minus dou p by dou y, here p is equal to u, that becomes dou u divided by dou y into dx dy plus I into double integration over r, and in the second integral p is equal to v and q is equal to u. So therefore that becomes dou u by dou x minus dou v by dou y dx dy. Now it is equal to double integration over r. So here it is given that f of z is analytic. F of z is analytic means that will satisfy the CR equations. So therefore here minus dou v by dou x is equal to dou u by dou y, right, and this one as it is into dx dy plus I into double integration over r. So here dou u by dou x is equal to dou v by dou y minus dou v by dou y dx dy. So now here dou u by dou y minus dou u by dou y is equal to 0 plus I into double integration over r dou v by dou y minus dou v by dou y, that is also 0 plus, so it implies that here the total becomes 0 because both the integrals are equal to 0, hence the total value of that integral is equal to 0. So therefore integration over c f of z dz is equal to 0. So this is the Cauchy's theorem, means whenever the given curve is a simple closed curve, then integration over C f of z dz is equal to 0 only if f of z is analytic at all the points inside and on the simple closed curve C. So, this is important for 5 marks, that is Cauchy's theorem or Cauchy's integral theorem. The next theorem is Cauchy's integral formula. So, here this is helpful to evaluate the value of the integral. So, instead of integrating the function, you can directly find the value of the given integral. So, here if f of z is analytic inside and on a simple closed curve C, and if A is any point within C, then f of A means value of the function at the point A is equal to 1 divided by 2 pi I integration over C f of z divided by z minus A into dz. So, here the value of the function at the point A is equal to 1 divided by 2 pi I into integration over C f of z divided by z minus A into dz. So, here 1 by 2 pi I is a constant and the function that should be of the form f of z divided by z minus A. So, here A is center of the circle, because we know that equation of the circle in case of that complex plane. So, that is given by mod of z minus A is equal to r. So, then z minus A is equal to what? R into e power I theta. So, that we have discussed in the previous class. So, now let us prove this one. So, here since A is a point within C right here. So, here we have considered the point A and this is the simple closed curve. So, means we cannot say that it is exactly a circle, any shape, but that should be closed and simple. Simple means the curve is not overlapped itself and it does not have any loops. So, therefore, that is called as simple closed curve. Now, here A is a point within C, then we can enclose it by a circle C1. So, here we have enclosed the point A by another curve, that is C1, but here C1 is a circle with center A and radius R, right. So, here C1 with Z equal to A as the center and R as the radius, such that, so here one condition is there, C1 lies entirely within C. So, here C1 lies entirely within C, means whatever we have considered the second curve, that should be within the first curve. Now, consider the function. The function f of z divided by z minus A is analytic inside and on the boundary of the annular region between C and C1. So, here this function f of z divided by z minus A is analytic inside the C, right, inside C and also in the region. So, here this is the region bounded by C and C1. So, in this region also the function is analytic. Now, we are going to use a consequence of Cauchy's theorem. So, here now by consequence of Cauchy's theorem, so here the statement is, if C1 and C2 are two simple closed curves such that C2 lies entirely within C1. So, here this condition is important, C2 lies entirely within C1. The second curve lies entirely within the first curve, and if f of z is analytic on C1, C2 and the region bounded by C1, C2, then integration over C1 f of z dz is equal to integration over C2 f of z dz. So means value of the integral will be same with respect to both the curves C1 and C2. So here we are going to use this consequence. Here C1 and C2 are such that the first curve contains the second curve, or the second curve lies entirely within the first curve. So it is our consideration. So here let us apply this consequence to these two curves C and C1. Now by consequence of Cauchy's theorem, integration over C f of z divided by z minus a dz is equal to integration over C1 f of z divided by z minus a into dz. So here our function itself is f of z divided by z minus a. So here C and C1, and consider this as the first equation. So now the equation of C1 can be written as, so here we know that C1 is a circle with center A and radius r. So then we can consider mod of z minus a is equal to r, then z minus a is equal to r into e power I theta, and z equal to what? A plus r into e power I theta. Then dz, so dz is equal to r into I into e power I theta. Since a is constant, so its derivative becomes 0 with respect to theta and z. Here into d theta, then theta lies between 0 and 2 pi. So therefore equation 1 becomes, so here integration over C f of z divided by z minus a dz is equal to integration over 0 to 2 pi. So here instead of C1 we are taking the limits 0 and 2 pi, because we are going to substitute z minus a is equal to what? R into e power I theta. So here f of z is there, so here z is equal to what? A plus r into e power I theta, that is z, and divided by dz equal to r into I into e power I theta, sorry, z minus a. Z minus a is equal to r into e power I theta, and dz, so here dz equal to r into I into e power I theta d theta. So here we have used the substitutions z, z minus a and dz. So now here r e power I theta, r e power I theta get cancelled, remaining I into 0 to 2 pi f of a plus r into e power I theta d theta. Now here this is true for any r greater than 0. So here r means that is the radius. So for any radius which is greater than 0, this equation is true. Means for integration over c, f of z divided by z minus a into dz equal to that I into 0 to 2 pi f of a plus r into e power I theta d theta. Now as r tends to 0, we get, so means whenever r tends to 0, that circle becomes the point A itself, because there is no gap or there is no distance from A to the circumference of the circle. If the radius becomes 0 means the point A itself is a circle. So therefore, now here integration over c f of z divided by z minus a into dz equal to I into 0 to 2 pi. Now here r is equal to 0, then this becomes f of a only into d theta. Now it is equal to I into f of a, that is constant, then remaining 0 to 2 pi d theta. Then this is equal to I into f of a. So integration of d theta is theta within the limits 0 to 2 pi. Then its value is equal to I into f of a into 2 pi, or it is equal to 2 pi I f of a, right. So here upper limit is 2 pi and lower limit is 0, so therefore that becomes 2 pi only. Now it implies that integration over c f of z divided by z minus a into dz equal to 2 pi I f of a. So from this equation we can write f of a is equal to, so f of a is equal to what, 1 divided by 2 pi I integration over c f of z divided by z minus a into dz. So this is the Cauchy's integral formula. So it is also important for 5 marks, the Cauchy's theorem, Cauchy's integral theorem. Then one more is there, Cauchy's integral formula for derivatives and generalized Cauchy's integral formula for derivatives. There are 4 theorems, means 4 theoretical proofs are there. So it is the Cauchy's integral theorem. Here f of a is equal to 1 divided by 2 pi I integration over c f of z by z minus a into dz, or this can be written as integration over c f of z by z minus a into dz equal to 2 pi I f of a. So in while solving the examples, so that will be given here, integration over c f of z divided by z minus a. Then we need to integrate this function with respect to z. So here instead of integrating, we can directly write its value as 2 pi I f of a, where f of a can be evaluated by f of z by substituting z equal to a. So that is the use of this Cauchy's integral formula.